So specific heat. The specific heat of a material is the amount of energy that must be added to the material to raise the temperature of a unit mass by one temperature unit. SI units of specific heat, represented by C, is measured in joules per kilogram Kelvin. What a bunch of crap that is. Specific heat is a number associated with an item that tells you how hard it is to raise the temperature of that item. Just imagine all these items stuck in an oven. Same amount of everything. You have same amount of aluminum, brass, carbon, copper, blah, blah, blah. If we have the same exact amount, we throw it in the oven for 10 minutes and we pull it out, which one of these items are going to be the hottest? Which are going to be the coldest? Well, the ones with the biggest number, water has the biggest number on this chart, is going to change the least. The ones with the smallest number are going to change the most. So lead would be the hottest temperature. If you put them all in at 70 degrees, room temperature, and you left them in an oven that's set for 400 degrees for 10 minutes, this lead is going to be the hottest one to touch. And the water is going to be the coolest to touch. So again, the specific heat is a number that tells us how hard it is to change an object's temperature. We have a formula for heat, and it involves that specific heat. Remember, that's C, joules per kilogram Kelvin. Right there it is. Specific heat of an item. That's a special characteristic of an object. All right, so to find how much heat energy an object contains, all we have to do is take the mass times that special number times the change in temperature, and we can figure out the heat energy involved. For example, there's a couple problems here I'd like to look at. This first one says a 5.10 kilogram cast iron skillet is heated. Did it say cast iron? It did. Cast iron skillet. My daddy used to use those. On the stove from 295 to 450. How much heat had to be transferred to the iron? Well, if you look down here at the chart, iron, iron, iron. Where's iron? Oh, there's iron down there. Stop moving. 450 joules per kilogram Kelvin would be the specific heat. So we could use our formula, and the mass is 510. The C is 450. And the change in temperature goes from 450, from 295 to 450, and you're minusing final minus initial to get that temperature change. So final would be 450 minus 295, and it's as simple as that. But watch out, this is to the tens. Now, why would they do something like that? Just to check and see if you're following your sig fig rules. So 450 minus this is to the tens, this is to the ones. When you subtract, you got to round that 155 number off to the nearest tens, which gives you 160. So now we're taking this times this times this, get our answer. Notice the units in specific heat basically cross cancel everything else. All that's left is a J. 370,000 joules would be the answer to this problem. Let's look at another one. The cooling system of a car engine contains 20 liters of water. Water is kind of special. It has a density of 1. Well, depending on the units, I guess. But anyhow, since 1 liter of water has a mass of, oh, there it is, 1 kilogram. That's because the density, volume equals mass. It contains 20 grams, 20 kilograms of water. All right, so that's what we need in our formula. We need the mass, we need the kilograms. What is the change in temperature of the water? Ooh, change in temperature, that's delta T. We're looking for delta T for this one. If the engine operates until joule number, that's your Q. So that's a K, so that's 1,000 times this. So we got 836,000 is our Q. So let's see, we have the Q, 836,000. We have the mass. Water's number is right down here, 4180. And then a delta T, which is what we're looking for. So take that 836,000 divided by 20, divided by 4180 to get 10. 10, I'll tell you, 3 sig figs all the way around. So if you used water, then your engine, no, the water temperature would only change 10 degrees with all of this amount of heat. Let's suppose that it's winter and the car's engine the car's cooling system is filled with methanol this time. Well, the density of methanol is given. What would be the increase in temperature in the methanol? So we're really comparing what's better for your car, water or methanol for this problem. Same amount of heat, what's going to happen? Do you think you're going to get a bigger temperature change or a smaller with that amount of heat? Well, we could answer that question if it's just bigger or smaller by looking at the number. Water is 4180. Methanol is 2450. Water will not change as much as methanol. So we should expect a bigger temperature change with the methanol. So let's see here, the methanol space. We got 20 liters of space. The density is a little different here. Got to do a little bit of conversion here. Let's take that 20 liters of space and we multiply it by, there's a 1,000 centimeters cubed in a liter. And then we got to multiply by the density of methanol and then multiply by the density of water. Why do we have density of water here? Kilograms. Oh, no, that's not the density of water. Density of water is 1,000 kilograms over a meter cubed. Scratch that. This is just 1 kilogram is 1,000 grams. And that gives us, oh, there we go. That's what we need. The mass of methanol. So the mass of methanol goes in for the M. That's a lot of conversions there to get the M. Where they all come from again? Let's look. This is the conversion factor to almost SI units. And this is the density of methanol, which is given 800, 3 sig figs. And then this is just kilograms to grams. All right, so anyhow, we got the mass. So we got the mass, we got the Q, and we know the C is 2450. So throw the numbers in there and divide. 21.3, just as I expected. The methanol is going to heat up a lot more. So which is the better coolant? Water or methanol? Well, of course, water, but we can't use water in our radiators in the winter. Remember, water expands when it freezes, breaking apart your radiator. So let's continue. How much heat is needed to heat 75 kilograms of, well, if we know how much heat energy is needed to heat a bathtub, then we can actually convert it into kilowatt hours. That's energy. And then we can convert it into money. How much money? We could ultimately ask, how much money will it take to heat a bathtub? Well, let's start with finding Q, and I'll show you how to convert it. So Q equals MC delta T. We're talking about water. Water is 4180 from the chart. So the mass is 75, the C is 4180, the delta T, go final minus initial. 43 minus 15, 43 minus 15 gives us 28 to the nearest ones, 2, and 2, reference number, don't count that as sig figs, and we got 8.8 million joules of energy. Now, in every 8.8 million joules, no, in every 3.6 million joules, it's a kilowatt hour. So how many 3.6s are in 8.8? Well, one way to do that is just divide that guy. Take that 8.8 times 1, what are we doing here? 1 over 3.6, and you'll get how many kilowatt hours. And then you multiply each kilowatt hour by 15 cents. And it takes, once you do all the cross-canceling, the J's are gone, the kilowatt hours are gone. The only thing left here is money. It takes a little more than a quarter to heat your bathtub water. I think I'm going to use more hot water next time. All right, enough. Let's go. All right, so last topic, thermal equilibrium. Thermal equilibrium states that the rate of energy flow between two objects is equal, and the objects are at the same temperature. That's when it stops transferring energy. So, hey, let's put our hot hands down on a cold desk again. If you put your hot hand on a cold desk, eventually the desk and your hot hand will become the same temperature. And that's what we refer to as thermal equilibrium. So I'm going to stop right there, and I will continue on the next slide with problems dealing with thermal equilibrium.